Okay, so my name's Tom Wickham-Jones, and I work at Wolfram Research, and I'm giving a talk about the Wolfram compiler, which is a new development project for working with and implementing the Wolfram language and compiling out to external code and making the code run faster and adding all sorts of great features. So the purpose of a compiler, or definition, it's maybe a system to translate computer source code from one programming language to another. Often it's going from a sort of high-level language to a lower-level language. Some of the benefits of compilation: you can get faster execution, so the lower-level language might be simpler and faster, and the translation process itself might sort of add optimizations, like removing unused code and stuff like that. It can work with other and emerging technologies, multi-core, other compilers, GPUs. You can get all sorts of verification warnings, understanding problems to, you wrote the code in some way that you didn't necessarily intend, and the compiler can give you some warnings about that, and it can help in cleaning and tidying code. So Mathematica's had a compiler since version 2 Mathematica, introduced in 1991, so quite a long time ago. And it's a very popular part. A lot of people reach to the compiler to try to sort of speed up the execution of their code. And I'm not going to go through all the sort of history of compile or show how it works. But it's been developed steadily over the years. The last big sort of improvement was in version 8, when we added some code generation and parallel execution features and a way of dynamically generating shared libraries to get sort of faster execution. So since then, I kind of thought that there's a lot of power in compile, but it also has a lot of weaknesses. And here are some of the weaknesses: that it only works, current compile only works for simple types like machine integer or machine real. And it doesn't support things like strings or association. And it doesn't support big nums or 16-bit unsigned integers. You can't add new types. It doesn't support function types and things that come with function types. It doesn't integrate with the pattern matcher. The implementation is hard to extend. Doesn't really use sort of modern knowledge about compilers and modern technologies. And it's kind of limited. It does have a code generation feature, but that's pretty limited. And it's not a very natural feature. And that's kind of why it's limited. So what's the solution? So the solution has been to start on a totally new implementation of compile. And this is a long-term project. And one of the things that's entirely built from the Wolfram language. So one of the language features that was added that kind of gave this a big impetus and a big kick was the addition of the association feature that came in. And association actually was version 10 or whenever. It's been a powerful feature, and I know from talking to a bunch of users in all sorts of other areas that it's added a lot of rev to the Wolfram language. So the general code flow that we get, I'm going to have to sort of shrink this down. You don't have to sort of read all of this, but this is kind of the flow that we. Sorry, trying to scale this. Well, I'll sort of scroll over. So we start with Mathematica code, and we go through some desugaring phase where we rewrite the code and we add various transformations, but at the Wolfram language code level. Then we translate into an intermediate representation, and this is something that's more written in the technology of compilers. We do type inferencing to add type annotations. Then we generate a we go through a technology called LLVM to generate a sort of target code, and then we have something that can be executed. So I'll try and show you some of these sorts of steps. So here I'm compiling out to the sort of intermediate representation. This is the sort of untyped. I might just shrink the size. I don't know if you can see that enough. So we've taken a Wolfram language program. So this is a function, like a sort of lambda function in Mathematica. It's been given type annotations for the input types, and then this is the sort of pseudocode, the Wolfram intermediate representation that comes out of it. And then we have a bunch of ways of looking at it. So this is another showing some of the sort of graph. So there's an if statement. So we have the if, and it's the true case or the false case, and then it comes together at this sort of final part here. Then we have another representation. So we take that representation and we add type annotations, and we also do some sort of expansions to target things like there are arithmetic plus operations here. And so we've added instructions here to get the target, the sort of the runtime functions. And we can see here that we've added, the sort of various type. So everything has a type all the way through, and at the very end we're returning an I. So this is returning an integer, and up here we have a markup that's saying we have integer, two integer arguments, and the return value is an integer. So then we have a next stage with this, and this is where we're jumping to this LLVM technology, and I'll talk about this. And this is another representation, but this is kind of the entry point into a tool chain that's called LLVM. And this is kind of like a platform-independent assembler code. And it can be interpreted, but it can also be converted further. And so LLVM is now a sort of really, it's kind of like the leading technology for implementing compilers. So the VM is kind of a bit confusing because it's not a virtual machine in the way that the JVM is a virtual machine. LLVM is like GCC. It's a compiler set of technologies, but it's a more modern, and it's designed specifically to be a set of sort of reusable components that sort of work together. It's the basis of the Clang C compiler. It actually comes from here, from the U of I. I think that's where the original work came, but it's now been picked up by many companies, and it really is an emerging standard for language support. And there's tons of tools that work with LLVM, like debuggers and transformers and profilers, and there are translators into other languages, like JavaScript, the Emscripten project, and it integrates with GPUs. So one of the things that we can do with LLVM is we can generate output code. So here I've compiled the function, and I've got something where I can execute it. So here I'm actually executing, the sort of native assembler code on the machine. So this is kind of a useful, powerful way to go. So I haven't gone through an object file and a library and a linker. I've just gone direct to a sort of layout of assembler in memory. So that's kind of useful. So I showed you the intermediate code. So we see that kind of here. And in order, so one of the details of this is in order to call this, you see this is taking an integer. But we're coming from Mathematica, from the kernel, and we have a different data type. We have expressions. And so the solution to this is we generate a wrapper function, and this is a bit more complicated, but so this is the function that we want to call, and this is the function that we can call from the kernel. And so this is taking like an exp struct, and it's doing various transformations to sort of pull out, do checking. You know, we check. It's a bit hard to see this, but you know, we're checking to see if this takes one integer, so we're checking the length is 1 and checking that it's an integer, and then down here we're actually calling the function, and there's some other sort of cleanup of this. So this is kind of a key part of the cleverness, is that we can generate this function dynamically. So for those of you who work with LibraryLink, this is also applicable to LibraryLink, because instead of having to write an interface thing that sits in the middle, we can now generate this automatically. So this is kind of the idea. Here's the kernel, and this is the function that we want to call, and we've created this sort of wrapper thing that sits in the middle. So, and this feature of generating code that we're injecting into the sort of pipeline is kind of a sort of powerful part of this, and that's kind of thing. So, you know, what can we do with this intermediate representation? I showed how we can execute it or something, but here, for example, I've converted it into the native assembler for the platform. So it's like, you know, Pentium. But one of the nice things about LLVM is it's very good at cross compilation. So here I've generated ARM instructions. So if I was on an ARM processor, I could execute that. And then here I can generate CUDA. So this is you know, code that could execute on the GPU. So I'm not going to talk a lot about CUDA. I'm not going to talk any more about CUDA in the talk today. But on Friday, Abdul is giving a talk where he's talking much more about running the compiler and targeting the you know, the sort of, you know, the GPU to execute the sort of native code. So another thing that you can do is I can export this to an object file. Oh, right, I already did this once, but so I just export it to an object file, and there's the, that's the, you know, the object file. So this file, I could then go and write a C program or some other language, and I could link it to this file here. And this shows one of the amazing benefits of using LLVM is that I just did this like on Monday morning, and it took me about 20 minutes to take the IR code and write it out, because there's a tool in LLVM that does that. So in the old compile, we added a code generator that did the same thing, and it took us, you know, about 2 or 3 months to code up the generating C code, invoking the compiler, compiling it, generating the object file. So a considerably, you know, if I say to you, you can take 20 minutes or you can take 3 months, I think you'll take the, you know, the shorter route. And that shows the benefit of working with existing technologies. Yes?
How independent is that file from the rest of the kernel?
Well, that file there is completely, I mean, like I said, it's just, well, you can see what it does. I mean, it's not doing very much.
What if you're trying to compile something that contains a function that is implemented?
Well, you need to satisfy all the functions that you're going to call, of course. So, right, so you need to have, you know, you'd need to have code for that. So I'll talk about that a little bit later. So now I want to talk about the type system. So the old compiler had a fixed set of types. They were like Booleans, machine integer, machine real, machine complex, and things that we call packed arrays. So they were tensors of integer, real, and complex. And that was it. There was nothing else. And so one of the things we really wanted was to have a more flexible type system. And so some of the benefit, you know, why do you want types? So they are, it's a type system is, in a sense, it's an additional programming language that you impose on top of your code, and it gets executed at compilation time. And if the execution of this language fails, it tells you there's something wrong. So it's a way of avoiding bugs and strange unintended code. And the type system is gives you a lot of introspection abilities, so it helps you to give correctness, to sort of rewrite and optimize code. And one of the ways that's been understood, and it's understood increasingly now, is the type system itself. If you make, with adding the right features, and generic types is one of the features, it's another layer of abstraction in your code that gives you sort of more flexibility. So you can write less code and do more with it. So that's some of the sort of benefits. So in the new compile, in fact, we have a pretty general type system where we can create types and add them and so on. And we've added a bunch of native types, Boolean, bunch of different signed and unsigned sizes. We've got compound types, obviously sort of packed arrays, but we have other types of compound things as well. We have function types, strings, expert, and parametric types. So let's have a little look at this. So I'm just going to show, this would be like a native integer. Here's a 32-bit integer. This would be a compound type, kind of like a packed array. So this is a packed array of rank 2 of integers. This is the sort of input syntax, and then we're creating, this would be a function type that takes an integer and returns another integer. And here we have this is a generic type. So this is a function that takes one argument and returns a type of that same argument. But we haven't said what that type is. So this is a class of functions that could take a real to a real, or a string to a string, or whatever. So for example, if you had an identity function, would have this type. So one of the things about the types is we have this sort of hierarchy of type, and this is how we add functionality to the system. So for example, the integer type, we have these things called subtypes or type classes. Not the same thing as classes in Java or C++. It's not the same thing. So like the integer type implements a bunch of, they're more like interfaces. And so we made we use this for debugging and understanding what we're creating. So we have this sort of type report that tells us what, so these are the sort of, concrete types. So these are the types that you can actually use in, pass around as variables. So this is like a 64-bit integer, which sort of appears down here. And these are all the type classes that it implements. So the value of these abstract types or type classes is that we can attach code to them. And so anything that implements the abstract type will pick up the implementation of that function. So for example, we have the floating type signature. So like many of the real types, and so that would be like real 32 or real 64 or complex, implement the floating, and so it picks up all of these functions like sort of exponential, and we have different sorts of types. So that's how we've the sort of type system. A lot of these things you don't really have to sort of worry about, but that's kind of how it works. So another aspect of type is we want to add type signatures to the functions, and we do this through what's called type unification. So here I've got a function type. So I've got, this is a function that takes an integer to an integer, and I want to match this with another function where I know what the input is, but I don't know what the output is. So I do unification and I get the substitutions, and the substitutions are saying that this output variable is a real, and then we could go and apply these substitutions, and the result is a function type that maps integer to real. So this is how we do sort of type inferencing. So, and this is done like in the Wolfram IR. So this is done, for example, here's a function. So we have u undefined for all the types, and then we run a type inferencing pass on the thing, and it's done this sort of unification for the function, and it's added the sort of appropriate type annotations. Right, let's keep going. So, but why do we have a type system at all? I mean, the Wolfram language is typeless. It's based on general expressions, the expression type. And on the other hand, this is quite beneficial as well. It saves a lot of coding time. You don't have to think too much about this. So why do we have that? So the solution that we've worked for here is to integrate expressions into the type system. So here I've written a function, and I've said that the argument here is a general, well, there's two arguments, but they're general expers. So I can call these with integers, and I get the result. But I can call this with symbolic input, and I get the sort of, it's calling a plus operator. Or here I'm calling it with sort of some big nums, and I get back, the sort of result. So this is working in the compiler system to get more to work with expressions. And working with expressions can be kind of useful when we go to integrate with the Wolfram system. So in the old system, we would just run compile, and we get back a compiled function. So that's what this compile to external function is doing. But in the new system, we can do things like I can write a function, and then I can do compile function, and now that's added an annotation to that pure function that uses the compiled code. So it works in the same, this one is the compiled one, and this is the uncompiled one. So then, if I use this function, so like in a function like the sort function, it executes with the this sort of optimized code. And actually, this is really nice. It's always bugged me that if I give a sorting function to sort, it executes more slowly. And experienced Mathematica programmers, of which there are a lot in this room, know all sorts of tricks that you can do to sort of, if you want to sort of use the sort of natural, the built-in sorting function, but have more complicated data. So, but this is, you don't need to do that. You just compile the thing, and you get, it's getting quite close to the, the sort of natural sorting. So that's kind of a nice sort of workflow. And here's another one, which is kind of a neat thing, is this is kind of new, so it's not really working. But the idea here is to compile actual down values. So I'm taking a function written as you would with pattern matching, colon equals. And now I'm compiling the functions, and it's generated. And this is one where I've got an implementation. One function here is calling another function. And then when I compile this, it's generated this sort of pseudocode, which I could then push out and execute. But this one here, you see, this function here is calling this function here. So this is not going through the pattern matcher. This is just making a direct call, kind of as you would if you've written a C program to do this. So this is kind of a sort of a neat thing. Or if you had another version of this, so I've added type annotations, and now the function that I've generated is going to come out. And if I save the intermediate, I could write this to the object file. So this one here is using functions from the runtime, but it'll pull those into the intermediate representation that you write out. So I could compile this and link it, and it would work. So that's kind of a neat thing. You've never really been able to do that, to write complicated programs with different functions calling each other and save them out in a way that could be executed outside of the system. So that's kind of a nice feature. I won't talk about this runtime. We've got a big, powerful runtime. This is another new feature that we added quite recently, and this is having sort of nested functions. So here I've got one function, and inside of it I've got another function that I'm using. And so we co-generate this, and it all sort of executes and works. Or here's a more complicated. I'm going to generate the output code. So it all sort of executes in the way that one would expect. Now this is really important because being able to pass around functions as data like this is needed if you want to do parallel programming. You need to generate intermediate functions and then use them in your code to do parallel processing. So this will open up a whole new suite of parallel computation that's not really been possible previously. So
is that red coloring intentional or something?
no, I maybe should have turned off. It thinks that these arguments are kind of repeated in some way. So no. Yeah, this one here is conflicting with this one, I would guess. So yeah, right. This is new syntax that's not added to the syntax coloring system. Right, so I think I probably need to wrap up since I'm coming. So this is kind of a just quick summary. So the compiler, it's a sort of pipeline of compilation, and we go through working with expressions and then generating this intermediate representation, going into LLVM IR, and then getting sort of executable code. We have a sort of type system, and as we go to the release, the things that we're looking to do is things like the down values computation. Even for the implementation of the pattern matcher, for many types of patterns, we can actually generate code like that wrapper function, and then we can compile that and execute that. And that would be a really powerful way to avoid having, when you write your code, even if you're calling the evaluator for the body of your code, you could select which patterns to use with a program that you don't write. We write that. And so this is a faster way to access your code that would be helpful if you had like small little functions. So all sorts of optimizations, integrations with technologies, and generating standalone code. So I think this is kind of an exciting technology. Thanks very much.